So we've talked about the gradient, which is acting out like the derivative. And the derivative is giving us information about how functions change. So the gradient should be storing a lot of information. And the answer is it does. There's a lot of wonderful information. Now remember, it's a vector, so there's things like direction and magnitude. And what we want to do is dig into the gradient and say, hey, what are some wonderful things that we can get from it? So that's our goal for today. Let's begin. So we're going to need two really good facts. Now, one fact is what we talked about in terms of directional derivatives, which says if I want to compute the derivative of a function, it's a directional derivative, so that capital D is a derivative, in the direction of u is a vector, for a function f at a point P, so there's a lot to parse there, but okay, it is the gradient of f at that point dot u. The key thing to remember, u is a unit vector, everything else, pretty straightforward. Life is good. Okay, so that's directional derivative, but we say, oh, wait a second here, that's a dot product. And what do we remember? Well, when we take a dot product of two vectors, we can find it by the magnitudes of the two vectors times the cosine, where the cosine of the angle, that's the angle between the vectors. So we can now say the following. The directional derivative in the direction u for the function f at the point P, which is the gradient of f dot u, is equal to the magnitude of the gradient of f, okay, so far so good, times cosine theta. Now here's the cool part. Cosine theta, it's a bounded function. Remember, cosine, it oscillates. It goes up and down between -1 and +1. So cosine theta is between -1 and +1, and therefore we have that our directional derivative is between, largest it could be, is the magnitude of the gradient. That would be if cosine theta equals 1. Smallest it could be is if we are negative magnitude of the gradient. So from just that fact, we get the following things. We say, look, what if we want to go in the direction of maximum increase? So we're like, up, up, and away. We want to go, fast, fast, up, up. Which way do we go? Well, the answer is we say, look, maximum increase would be when we have this directional derivative. And that would say, in order for us to achieve that, we'd have to have theta to be 0. Well, theta is the angle between the gradient and u. And so that says, look, the gradient is the direction we want to go. So the gradient vector, it's pointing in the direction of greatest increase. So in other words, if you want to go up as fast as possible. Now, what is the amount of greatest increase? The answer is the magnitude of the gradient. And so if I want to know the direction of the greatest increase or the magnitude of the greatest increase, then that's all about questions about the gradient. And so, indeed, oftentimes you can say, if I want to know the gradient, I can say the gradient of f is determined by knowing the following two things, and namely max amount of increase and direction of that increase. So, because remember, gradient is a vector, and all vectors have two parts. And so as long as you know those two parts, life is good. So max amount of increase and the direction of greatest increase. So in particular, if you're seeing a problem and you say, this problem mentioned things about the greatest increase, then you're like, aha, I know which way we're going. Whoops, I forgot to write the word greatest. Okay. So anyways, if you see any problem that talks about in the direction of greatest increase or the maximum amount of greatest increase, it's really a question about the gradient. Now we can go backwards, which is negative the gradient. That points in the direction exactly opposite the gradient. So like if gradient points this way, negative gradient points that way. So they're pointing opposite to each other. And that would be where theta is a half revolution. So in other words, theta is pi, which means cosine theta is -1. That's where we get that minus. So minus the gradient is a vector that points in the direction of greatest decrease. And of course, no surprise, negative the magnitude of the gradient is the amount of greatest decrease. And there we go. Now, that's amazing, a really beautiful thing. And it's so intuitive. It's like, okay, if I know my partial derivatives, I should follow wherever they're pointing to. That should tell me the fastest way to go. Now, there is kind of an interesting idea here. And if you look in some places where they do optimization, you'll see this notion called the gradient descent. And what is that? Well, descent says you want to go down. So oftentimes when you hear something about gradient descent, it's like I'm trying to find a minimum. Well, how do you find a minimum? Well, one way to do it is to say, let me just start somewhere and let me head downhill. And so the idea, it's a very simple idea. Now, we're not going to do that. This is not the point of our class. But you know what? It's fun to learn stuff, right? It's like, hey, cool, free learning, for sure. So the idea is to say, to find the min, or maybe I should say to find a min, because that's what we're after, is start somewhere and go downhill. Now, how do we go downhill? That's where the gradient comes in. What we do is we say, well, let's see which way the gradient points, and we'll go in that direction. And so, in essence, you go a little bit, not a lot. You say, okay, now I've moved a little bit downhill. I should be careful here. Going in the direction of negative the gradient, right? Because we're going downhill. So if we want to go uphill, go the gradient. If we want to go downhill, go negative the gradient. And so we say, all right, just start moving in the direction negative the gradient. Okay, go down a little bit. All right, now where are you? Now go again, direction negative the gradient. Okay, and keep going, And that'll help you keep going down and down and down and down. Unless, of course, you end up at a minimum. And if you're at a minimum, well, the gradient is 0. And you also can't go down. So that's how gradient descent works. It's actually just a really simple idea. It just says, okay, go downhill. Isn't it? It's like, wow, these math ideas aren't so bad when you just say things like, go downhill. Yeah, okay, that'll help me get to a low value. It's not so bad at all. So anyways, moral is gradients are really cool. And you might say, fantastic. Can we get anything else? And the answer is yes. If you act now, we'll throw in one more property of the gradient, free of charge. You're like, wow, more? How awesome could gradients be? Well, this awesome. So we'll go back to the notion of level curves. Now, what are level curves? It's probably good to remind ourselves what they are. The idea of level curves are you have some surface out in space. So this is a surface here, and you can see there are some parts that go up, some parts that go down. And the level curves are you slice at a height. So you can imagine I have this plane here, z equals k. And I look at the plane and I ask, where does it slice the surface? Well, it slices it, and when you slice, what you're going to see is you're going to see some curves. So that these curves here are where we're slicing into our surface. Well, they correspond to curves in the plane. So these are level curves. The idea of level, saying as I'm on the curve, I always stay the same output. If you think about it in terms of like a hiking, if you're out hiking on these surfaces, you're at the same elevation, so you don't change. And that's the key idea. So if I'm walking along, and suppose I were to stroll along this level curve, so here I am walking along the level curve, what's happening to my elevation? The answer is I'm not going up, I'm not going down, I'm staying level. So there's no change in my elevation. So in terms of the derivative, no change corresponds to 0. Now, what do we see? Well, if you were to zoom in, of course, on this level curve, what you would see is that close by, our level curve looks like a line. So if we have our point here, P, it says if I want to stay and move in the direction that's on the level curve, well, that's just moving on that level curve. I'm going to be 0. 0 change. So moving back and forth on the level curve, 0 change. On the other hand, if I want to go steep as possible, well, you have to look at the picture here. So in the picture, you see that we're going uphill as we head in towards the corner. So that our gradient points that way. So the moral here is if we know our directional derivative is 0, and we say, oh, the directional derivative, remember, is the gradient dot a vector. Well, it's the gradient times the cosine of something. Cosine being 0 means perpendicular. So, our cool fact, the gradient is perpendicular to a level curve. Every level curve. So no matter where I take the gradient, I'm going to say the gradient at that point will be perpendicular to the level curve that passes through that point. Now you might say, okay, well that's a fun fact, but why were you so excited? Because you were just like, ah. And here's where we get like, ooh, this is good, this is good. We can talk about not just level curves, we can also do level surfaces. In other words, ideas translate, not just to functions of single variables or two variables, but functions of any number of variables. So we can say, what if I have a surface W equals some function g of x, y, z? So now I have this surface, well, whatever it means by a hypersurface perhaps, out here in 4-dimensional space. Well, what I can conclude is that the gradient of g of ABC is perpendicular to any level surface. Well, that would be g of x, y, z equals k. So why is this cool? Well, you have a perpendicular to a surface. You say, all right, so why is that useful? Well, the moral is gradients are normal vectors to the level surface. And really what that says is, aha, the gradients are the normal vectors for tangent planes. And now we're like, whoa, that sounds nice, because it sounds like it's going to be really easy to find normal vectors to tangent planes. And that's because it's going to be really easy to find normal vectors to tangent planes. Ah, this is a great day for us. And so how does that work? Well, that really gives us a second option to finding tangent planes. So let's take a step back and do a quick review. How do we find tangent planes? So we're going to have two methods. Now the first method says, suppose you have something of the form z is a function f of x, y, we find partial derivatives. So we compute partial f partial x at ab, partial f partial y at ab, and we have our tangent plane is the function at ab plus partial derivative with respect to x at ab times x minus a plus partial derivative with respect to y at ab times y minus b. Fantastic. And it works. And it's beautiful. Method 2 says, well, wait, what if you have a crazy surface? So it's not like z equals f of xy, but maybe it's like f of xyz equal to some constant k. And we've seen expressions like this before. You might think of this as an implicit surface. In other words, this is a case where we can't actually write and solve for z equals something. The great news is we can now still take derivatives and, we can still find tangent planes by taking our collection of partial derivatives, and life is good. So how do we do it? Well, we compute the set of partial derivatives. So we talk about, what does this look like? This is our partial capital F with respect to F, X partial of capital F with respect to Y, partial capital F with respect to Z. Evaluate at that point, so we get a vector. Remember, it should be numbers. We don't want functions, because what we want to end up with is a plane. A plane needs to be something that looks flat. Make sure to remember to evaluate. So the nice thing is, easy to find a normal vector, and we say, look, that's our normal vector, and then if we start with x minus a, y minus b, z minus c, we get 0, because that's how we find normal vectors to planes and how we find planes. Cool. Well, this is fantastic. Now, you might say, these are two different ways. Are they compatible? And the beautiful thing is, yes, they actually give the same answer. So suppose you set your function, capital F, to be f of x, y minus z. So in other words, you subtract z across from here. Now take your partial derivative. So f sub x, f sub y, minus 1. So at our point, a, b, f of a, b, we have our f sub x, f sub y minus 1 dot, x minus a, y minus b, z minus f of a, b equals 0. And if you expand and rearrange, lo and behold, you get the same formula as before. So you're probably thinking, cool, so method 2 does more. And you're right, it actually does more. It is a more universal statement. Everything you can do with method 1, you can also do with method 2. That being said, know both. It doesn't hurt you to know both, because it just depends on context. Do you have a function of the form z equals something? All right, use the method where you just compute the individual partial derivatives. Do you have an implicit surface? All right, use our gradient method. But the nice thing is, now we can find tangent planes. And of course, that brings us sort of to our last small topic for today, which is, well, why would we want to find tangent planes? And really, one of the core things we come down to when we talk about tangent planes is to say, we can use tangent planes to do what's called linear estimation. Now, the word linear is just a really fun and fancy way of saying flat. So when we talk about things like linear estimation, what we're really talking about is we want to approximate with something which is flat. We say, well, why would we do that? Well, it's very easy to do evaluations with things which are, like a plane. It's very easy to carry out the computation. So we like that. And so we can say, if I have something which is very complicated to carry out the computation, I'll replace the complicated thing with a flat, easy thing, which is not a bad approximation. So what we end up with is we say, look, our function minus the value at ab, which is our change in z, is approximately f of x at ab times x minus a, f of y of ab times y minus b. And so this is just saying, if you want to understand what's happening to your function, so say, well, how much does the output change? Well, if I want to know the change in my output, I look at things like, take the rate of change in the x direction times the amount of change in the x direction, plus the rate of change in the y direction times the amount of change in the y direction, add it all together, and that gives me an estimate for the total change, and so forth and so on. Now, you may occasionally hear people talk about differential notation, and differential notation basically says, instead of saying, well, what's happening approximately with the surface, differential notation just says, look in the plane, what's going on? Because nearby, the surface and the tangent plane are indistinguishable. So that's where the dz notation comes from. dz is f sub x dx plus f sub y dy. And the moral here is to say, look, if I have the plane, I can use my plane to approximate. And so I can replace a complicated computation by a simple computation. Use the plane. Use the plane. Good. Good. Well, let's go and do some practice. Hope to see you soon.